Hello physics students, and welcome to our next video in our unit on forces. This video is going to address two types of forces. Gravity, here the force of gravity. When we talk about gravity, we're going to look at mass versus weight. We're also going to look at the normal force. It's abbreviated F sub n, and we're going to see what that is and do some calculations with that. First, let's talk a little bit about gravity. Newton's universal law of gravity, it states in the definition of gravity, it's the force between two objects, and it depends on their masses and the distance between them. So you can even just think of this from your knowledge about gravity. If you have objects that have different mass, there will be a much greater force of gravity for this object with the greater mass than for this object would have less of a gravitational force between it and the second object. If we look at distance, if two objects are closer together, we know that they experience a greater force of gravity between them than if objects are further apart. So let's look at the mathematical relationship specifically between all of these. That would be the equation, the universal gravitational equation. The force is equal to the gravitational constant times each of the objects' mass 1 times mass 2, and that is divided by the distance squared. So you can see that both the distance and the mass of each of the objects has a great effect on the amount of force that exists between two objects due to gravity. So why do you feel the Earth's gravity but not the Sun's gravity? Why aren't you pulled toward the Sun? Why are you pulled toward the Earth instead? Well, you're a lot closer to the Earth. Remember the distance factor here. When it comes to the force of gravity. Another question, why don't you feel the gravitational attraction of your pencil or your car? Well, because the mass is much, much, much less. So just remember that the force of gravity depends on both the mass, the greater the mass of the objects, the greater the force of gravity, and it depends on the distance. The greater the distance between the center point of each of the objects, the less the force of gravity. Again, gravity is a long-range force, meaning that you never actually entirely get rid of it. There is always some distance between two objects. The distance may be incredibly large, but the distance is there nonetheless, so you never actually entirely get rid of the force of gravity. So you already know this, but near the Earth's surface, G equals 9.81 newtons per kilogram or meters per second squared, and that value of G decreases as you travel away from the Earth's surface. And then obviously near the moon's surface, G is much less than near the Earth's surface because the moon has much less mass. So it's important to know or remember that weight is not the same thing as mass. Weight is actually a measure of the gravitational force exerted on an object. So when you stand on that scale, you are measuring the force of gravity that is being exerted on you. Mass is something very different. Mass measures the amount of matter contained in an object. Obviously, if you increase your mass, you will increase your weight as well. Because there will be more mass. Remember, weight is a measure of force, and if force equals mass times acceleration, increasing your mass will also increase your force. My weight on Earth is around 560 newtons. If I were to stand on the moon, my weight would be 90 newtons because there would be less force. My mass is always the same. It's 56 kilograms. So when we are calculating weight, which is our force, or which is the force exerted on us by gravity, we're actually calculating the force of gravity on us And the equation for that is force equals mass times acceleration all the time. And in this case, the acceleration will be the acceleration due to gravity, or g, 9.81 meters per second squared. Pounds is also a unit of measurement for weight. It's not the SI unit. It would be the English unit. Newtons is the SI unit for weight, because it's the unit for force, and weight is a force, is a measurement of force. So here's a little example. On Earth, what's the weight of a large screen TV that has a mass of 75 kilograms? Well, let's write down what we know. We know mass equals 75 kilograms. We can use our equation force equals mass times acceleration. In this case, the force of gravity equals mass times acceleration due to gravity. So we also know acceleration due to gravity equals 9.81 meters per second squared. So we can just plug our values in here. So the force of gravity, which is what we're measuring when we want to know the weight of something, is equal to 75 kilograms times 9.81 meters per second squared. And when we multiply that together, remembering sig figs, we actually get 640 newtons. Kilogram meters per second squared is a newton. And that brings us to the second force we're going to look at, and that is the normal force. So here's a question for you. If the force of gravity is acting on the book, why does the book not continue to fall toward the center of the earth? It was pretty obvious, but let's do an analysis of the forces acting on the book and draw those in. We know that the force of gravity is acting in this downward direction. We know that the table is also exerting a force in this upward direction on the book. That is why the book does not continue to fall toward the center of the earth. The force exerted on the book by the table is called the normal force. And let's take a look at why it's called the normal force. Normal can also mean perpendicular. And the normal force is always perpendicular to the contact surface. Here we can see when we draw our normal force in that it is perpendicular to the contact surface. It makes a 90-degree angle with the contact surface. It's important to remember the normal force is not always opposite the direction of the force of gravity. It is in this case obviously opposite the force of the direction of the force of gravity. But let's take a look at an example where the normal force is not in the opposite direction of the force of gravity. So remember our example in one of our previous videos where we had a book on a drafting table. We have a physics book resting on a drafting table. And in that picture, if you'll recall right here, the forces that are acting, here we have the force of gravity down, we have the force of friction this way. This force of the table on the book is actually the normal force. So I wrote that in here. We just didn't call it that then. We hadn't defined that force yet. And it follows that first definition. The normal force is perpendicular to the contact surface, which is the table in this case, and makes 90 degrees with the table. So that's why it's the normal force. In this example, however, the normal force is not opposite the force of gravity. The force of gravity is at some angle that's not 180 degrees from the normal force. The normal force is equal and opposite to the component of the force of gravity that is perpendicular to the contact surface. In other words, if we were to, let's say, select an XY coordinate system for this, and let's say we make this the X direction and this one the Y direction. If we were to do that, we could say that the Y component of the force of gravity is in the opposite direction of the normal force, because this force of gravity has both a Y component and an X component. Because the normal force is not 180 degrees from the force of gravity, the normal force is equal to mass times gravity times the cosine of theta, because it's not at a parallel angle. It is, indeed, there is a different angle here. In this case, this is actually true for all forces. When they are not parallel to one another, this is how we can calculate them. Theta, in this case, is the angle between the normal force and the imaginary vertical line, or it could also be the angle between the contact surface and the imaginary horizontal line. I'm going to redraw this on the next frame for us. So when I redraw that, theta can be the angle between the normal force here and the imaginary vertical line, or it can be the angle between the contact surface and the imaginary horizontal line. So it can be either one of those. Here's a little review, what we've discussed. The difference between mass and weight. Make sure you can calculate weight if you're given the mass of an object and you know the gravitational strength. And you know that for Earth, obviously. Also be able to find the direction and magnitude of normal forces, and you'll get to have a little practice with that, with your problems. Here's some advanced ideas. Feel free to read through those and come up with some ideas on your own if you don't like any of those. So ask some questions, and I look forward to seeing you in class.